Section 4.3, derivatives of inverse trig functions and derivatives of inverse. We started just by taking a look at Theorem 1. If f is differentiable at every point in an interval and the derivative does not equal 0 anywhere in that interval, then f has an inverse and the inverse is also differentiable. Just a theorem that we can use that allows us to take the derivative of the inverse. Alright, here I've worked out the derivative of arc sine with some steps written out. You're asked to find dy dx if y equals arc sine of x. We need to remember that arc sine means the angle whose sine is whatever x is. So the first thing we do before we can differentiate is do a rewrite. If y is the angle whose sine is x, that means that sine of y equals x. That's the important rewrite before we can take the derivative. Now we can take the derivative implicitly, getting cosine y dy dx equals 1, and then solve for dy dx, and that is 1 over cosine y. We want a function of x. Right now we have a function of y. We have dy dx equals secant y. So we go back up to our original rewrite, and we make a right triangle based on that relationship. Sine of y equals x over 1. And sine is opposite over hypotenuse. So we make the opposite x, the hypotenuse 1, and the angle y, and then we use Pythagorean theorem to find the missing side. 1 squared equals x squared plus question mark squared. We're looking for the question mark, so to solve that we get the square root of 1 minus x squared. And then if we want to write secant y as a function of x, we note that secant y is hypotenuse over adjacent. Hypotenuse is 1. And adjacent is the square root of 1 minus x squared. So the derivative of arc sine is 1 over the square root of 1 minus x squared. This is the process we will use for every one of our inverse trig functions. And if it is a composition function, where the inside of the function is not just x, we can apply chain rule. So if I'm taking the derivative of arc sine of 7x squared plus 5, I will have 1 over the square root of 1 minus 7x squared plus 5 squared times the derivative of the inside, which is the derivative of 7x squared plus 5, or 14x. All right, and you'll get practice finding the derivatives of the other inverse trig functions. And then I wanted to talk quickly about the methods for finding the derivative of an inverse at x equals k. The first thing that we can do is we could find the inverse function and then differentiate. So if we had y equals x squared, we could switch the x and the y and solve for the new y. Here we get plus or minus square root of x, which is not actually a function. But if we limit our domain to be from 0 to infinity, then this would work and it would only be the positive root. Let's fix that. There is our inverse, and then we could find dy dx by just taking the derivative of that inverse. Simple enough. Some functions are too difficult to find the inverse, so we need another method, and that's what we have here, method 2, where we will switch the x and the y like we do to find the inverse. Then we will implicitly differentiate, solve for dy dx, and here is the only little twist. We need to go back to our original problem in number 1, our inverse function, and we want to replace the value of k for x in the inverse function from step 1 and solve for y. So we're plugging in the x value that we're interested in and solving for y, and then we plug that y into our derivative. So for example, if we are asked to find the derivative of the inverse at x equals pi. For y equals x plus prime x. So the first thing we do is we switch the variable, and we make x equal y plus sine y. And now we can take the derivative implicitly. We get 1 equals dy dx plus cosine y dy dx. We solve for our dy dx by factoring it out on the right side and then dividing by 1 plus cosine y. And we get a dy dx equal to 1 over 1 plus cosine y. And then we go back to step number 1, and we want to plug in our x value and solve for our y. We'll need a little help with our calculator here. We plug in pi for x equals y plus sine y. And if we solve that using our calculator, we get y equals pi. And then we plug that pi into the derivative of the inverse for the y value. So we have 1 over 1 plus cosine of pi. In this case, we happen to get 1 over 0, so the derivative of the inverse does not exist. So let's look at another example where it does exist. This time we're given y equals x cubed plus 5x minus 1 at x equals 5. We want to find the derivative of the inverse at x equals 5. So again, we switch the x and the y. Then we take the derivative implicitly, factor out our dy dx, and solve for dy dx, and we get our derivative as 1 over 3y squared plus 5. We go back up to number 1, and we plug in our x value here, and we solve for our y. Again, we'll need our calculator to help us there. And when I say that, I just put 5 in y1, and I put y cubed plus 5y minus 1 in y2, and I find their intersection. Okay? All right, once we have that y value, we plug that into our derivative here, and we get 1 over 3 times 1 squared plus 5, the quantity. And that is 1/8. So the derivative of the inverse of our function at x equals 5 is 1/8. So there's your practice on derivative of inverse trig and derivative of inverses.